So I realized this morning after I posted the quiz, I never said like make visible to students. So now it's visible, like it's no longer invisible, that'll help to actually look at the assignment. But it's up there, and I mean, we had kind of worked on it together on Friday anyway. So hopefully it's what we talked about, because I took our conversation, turned it into like physics problem, right? Spring, go up a ramp. Yeah, that's the first thing for today. I don't know why the default is when you add something that it's invisible, like only visible to you. It's like, why do you think I'm adding this if I want it to be only for me? I already decided to put it onto Husky CT. Anyway, such as... Okay, we're done with homework. This is the last project, at least last one that I'm saying, like, do this project. I think it's important. And the idea of it is that it's this yo-yo de-spinning, it's a space like flight mechanics kind of thing. It's pretty cool. And let's see. That's weird. A YouTube. So it's like a GIF of the yo-yo de-spinning mechanism. So it should repeat in a second. But like general idea is like when you launch a rocket, no matter how well everything's aligned, like things will start spinning. It's just if there's any small torque, whether it's from air or the fact that the rockets can't be perfectly in line with your center of mass, you'll start spinning. And yo-yo de-spin is a very low, like you don't need any control mechanisms, you don't need a PID, like nothing. Like if you have fishing wire and those lead masses, you can build this system. And you have some kind of release mechanism, it releases it and it stops the spinning, at least as best as you can get. So we're gonna design our own yo-yo de-spin for some kind of payload. But pretty cool. As like one analog of this, or one like way to think about it is like, have you ever been on the playground and you spin around on a merry-go-round? Like as you like bring yourself out, the whole thing slows down. But you can do usually it's more fun to do the opposite of like when you pull yourself in, now you spin real fast. We're trying to do the opposite thing of like get mass away from our system so it slows down, so it's no longer spinning, and then cut the cord so it just disappears and go. We don't really care what happens to our yo-yos after the fact. And just because politics are fun, we can look at a Tesla Roadster of de-spinning this Roadster. Maybe this is Trump, hopefully, in space, just anywhere that's not DC. Who says engineers don't get involved in politics? We launch politicians into space all the time. Safely. We're going to de-spin him so he doesn't throw up. And that'll be nice. Everybody wants. Oh, you want to keep the spin? All right, so then we'll do a yo-yo spinning. We'll launch him with yo-yos out, pull them in, and then it spins faster. Yeah, you got to throw up. So I'll pull up the Nano Hub version so we can kind of run, so I can run through like a tour. Main thing for today is pick a payload and then make some kind of some estimation of what its moment of inertia would be, because that's our main design parameter. Like once we have that, then we can start picking like how long does the rope need to be, how big do the yo-yo masses need to be, like all this other stuff. So again, we have like our main kind of Python setup variables, at least for our Roadster with a politician in there. It's 1.2 thousand kilograms. I'm making this assumption that it is a block. So like whether it's a car or a brick, they look the same in terms of my dynamic simulation. It's just m/12 width squared times height squared. At the end of the day, it should be some kind of like mass times distance squared. And you can use whatever units you want. Normally, SI units is kilograms meter squared. That's your moment of inertia. So we're going to estimate something. In this case, a car is a block, solid cuboid. But there's tons of other. Here, let's open the link. We can't really do a point mass because a point mass spinning around its own axis has 0. I guess you can do that. It's just, it wasn't spinning before and now it's not spinning after. You don't care. It's a point. It's just one point. But if you have like two masses, you can figure out like how those things are rotating around each other. If you want to send a baseball bat into space, as if you like hurled it and then you want it to stop spinning. Okay, so we're setting up that. We have W0 is like our initial, and I think I changed this. I think initially it's like 10 1 kilogram? I don't know. Does anyone have a number in theirs? I guess I do, right? 0.01, so 10 grams. That's what I'm using. So let's define that. There's some setup stuff for this simulation. I think this is initially like 0 to 1 and maybe 100 steps or something. Let's do 101. We get a plot of the path of the yo-yos. First off, what is a path? Like, what does that mean? Yeah, it's a plot of like its XY location. So like where did it go? That's what the path, and it is like a physics thing to say like what was the path of this thing. But this is the path in relation to the driver, like whoever's sitting in that driver's seat, this is what that person would see. So according to them, they would start the yo-yo D-spin, and there's one on their right, one on their left. It would spin up and over their head, and then up and over their head again, and then to them it would look like it's like disappearing in a straight line off into the distance. And if we keep simulating, it actually looks like it starts moving the opposite way, but that's something else. Well, if we continue, this is just looking to the point where we cut the cord. So like at that TF, we would say like, done. Like cut that cord, let it move on. And that's what this plot is showing, is we have how fast our driver is spinning, so how fast the payload is spinning in a circle, and time, so how long it took to get to that point. So in this case, after 0.6 of a second, this whole thing's over, and the cord would cut, and these things would shoot off into space. And that's the end of our like design parameters. If we're over designing this, like so let's see, 0.61 seconds, it all happened. If I said like, well, just for safety, I'm going to add like an extra 3 meters of cord and let it run till 0.8 seconds, that would result in my car starting to spin the opposite direction. Because I went from a positive 15 to now like a negative 4 radians per second. So positive, negative, that matters here, because we really, the absolute value is all we care about. We don't want to spin. So if we hold on to it longer but keep the cord running out, then we did the opposite effect. Now we're just spinning in the opposite direction. Not as good. So there's a couple of questions, and we can get to we can either talk about them today or next time about like, why is this becoming negative? Like what's happening here? And then some other things are more like design changes of like, if you're changing mass of the yo-yos, what else is changing? Does the time matter? Does the length matter? Like what are the things that we need to consider in this design? So since the second question is mass of the yo-yos, let's try changing the mass. Right now they're 10 grams, and the whole thing takes 0.6 seconds, so 600 milliseconds to run. Do you want to make them bigger or smaller? Bigger? It's more expensive. It's all right. We can afford it. We're sending a Tesla into space. How much bigger?
3 times.
3 times? So like space, like so the reason I said it's more expensive is like there is a number. It's gotten cheaper over time because we're sending more and more like garbage into space. So it's like getting pretty cheap to send whatever garbage you want into space. But I think last time I looked, it's like, it's not exorbitant, but I think it's something like $100 or $150 per pound to get something in, if you're already on a mission. To get a mission, there's already like, if you're gonna send anything into space, even nothing, that's a lot of money. But for every extra pound, I think it was around 100. Like it was a lot less than I thought it would be, like hundreds of dollars rather than, I assumed it would be thousands. We could look it up. All right, so it's 3 times the size, but we got money to spare. We'll make it bigger. And okay, so here's the path. I haven't run it yet. This is what our path looks like with 10 grams. So we'll make it 30. And ta-da! Not much. I mean, roughly it's still, now it's kind of doing like 2 1/4 rotations rather than 2 1/2 rotations, like slightly less. And then, so here we start at 15, go down to 0 at 0.6. Now we get to 0.45, so everything's happening a little faster. Like we have 3 times as much mass. Things go faster. What do you think about the length, the cord length? Is it going to be shorter or longer? We saw that there's less time. It's going to, like, it happens faster because it was 0.6 seconds, now it's 0.4 or something, like less than 0.5. What do you think? More cord, bigger mass, more cord? Bigger mass, shorter chord. Shorter makes sense, right? Because radius times angular velocity, that's our moment of inertia. So if we, and then times that mass. So we increase mass, we should be able to decrease radius. Sure enough, 3 times the mass gives us like 4 meters less of like fishing line or whatever, probably some kind of like space age fishing line. Cool. What if all right, so we know bigger mass, less chord, things happen faster. What if I'm moving faster? Like, because this is just a case where it's 15 radians per second. So that's like 2 rotations per second. What if it's more like the video that we saw where it's more like 10 rotations per second, like 10 times this, right? We're spinning real fast. Is that going to change everything here? Like, do we need a different yo-yo system for every speed that we're rotating? Let's test it out, right? So let's go from 15 up to 150 radians per second. So we're moving 10 times faster. Our path looks kind of wacky. There's only like 1, 2, 3, 4, 5 data points, because most of the time that we're simulating this is past the I'll be there for senior design oral 2. It's happening. I know it started, but I got stuff to do too, right? So if I want to see like what the path is when things are moving faster, I need more time, like make it 1,000 data points. It's not going to change my analysis, but just so I can see like what's happening. Kind of looks like the same thing, right? Like as far as the path of what relative to our driver, it's still gonna like come around their head, go under the car, and then up and over again. So nothing really to write home about. We're moving faster, so we're at 150, and it shoots down to 0 in less than 1/10 of a second. So this is all happening, and that's kind of what we saw in the video too. Like when you release this thing, it happens fast. Everything like comes to 0 rotation very quickly. Okay, so what do we think? Time definitely went down. Do you think the length is going to decrease or increase? Increase? What do we think? Some increase. Do a thumbs up for increase, thumbs down for decrease. Thumbs up, maybe increase. Everything's moving fast. It seems like it, right? Moving faster, more angular momentum. Maybe we need more chord. Moves faster, but the chord is the exact same length. This is the real like magic of this yo-yo D-spin mechanism. It doesn't matter how fast you're moving. If you have the right size chord for your payload, it'll stop you. It'll bring you to a stop, which is pretty awesome. Because otherwise you would need like reverse thrusters or something to kind of stop you from spinning somehow. Or something else. I don't know. You can do all sorts of stuff. Yeah, magic. All right, so those were my kind of experiments, at least for today, for this analysis. So what I wanted to do for the rest of the time was pick out your own payload and then try to de-spin that. So that could be, and so I've seen the crazy ones that I've seen were Death Star. Like if the Death Star is spinning and you wanted to despin it, what would that look like? Like how many miles of cord do you need to get this thing to stop spinning? Or someone was really into like World War II history, and they thought like, all right, if I take one of the submarines, launch it into space, do I have enough anchor line to stop the thing from spinning? And then, I don't know, land on another planet? I'm not sure what the end game there was, but it at least would not be spinning. You can move on to the next stage of your plan. And then some other ones are like a cow or a baby brother. That one, I was like, what? And they're like, don't worry, I put him in a capsule, like Superman. I'm like, okay, all right, that's fine. So we need a payload and some estimate for moment of inertia, and then we can start figuring out like, what does your yo-yo D-spin look like? How long of a cord? How big does it need to be? These kind of things. Sound like a plan? All right, cool. Yeah, and one way to go about it is just like, well, how could I fit a shape that is a cylinder into this? You can kind of do it the engineering way of like, what looks like this shape? Or the other engineering way is like, pick something and then start building like Boolean additions of like, is it a sphere plus a cone, or however we want to do it? Is it a plate? All sorts of different ways. So we're trying to find payload, moment of inertia. Oh yeah. Fish. So yeah, like an oval. So like people make fun of physicists for saying like cows are spheres, but really like it's a surface to volume thing. Like biological things in general try to maximize surface area for a given volume. And so we all end up with like kind of like spherical sort of things at the end of the day. To maximize surface area for our given volume. Yeah, we can do like an ellipse where you put like a plate. Stop the Earth? Yeah, we will.
And how big would the mass have to be? Like that much. And like this how big the strange probably like relative to like the solar system was
It is, yes. It's pretty big. And there's also the other limitations. If I assume the gravity between D-spin and the Earth, it's just negligible.
oh, because it would pull in. This is too low.
Yeah, it's like technically we're all on D-spin. If we sent like everything off, we would D-spin it a little bit. And every time we send a rocket, D-spinning the Earth. But I mean, it's totally fine.
Yeah.
It's a thought experiment. Like, what if we could?
Yeah,
Because you could imagine, have you heard of the space elevator?
Yeah.
Okay. You could imagine like, if we had stuff in the space elevator, we need to stop the Earth spinning and just keep
like see how much
sending stuff out.
how much mass we have in space distance of like that many hundred miles.
Yeah.
How much mass we have to have.
Do you think the fish would spin on its end?
That would work.
Back to my dimensions of the fish.
Do you think it should be rotated in the center or the edge?
So for free spin, it's gonna rotate around the center of mass. But there's also this question of like, is it corkscrewing? Or is it head over tail? Or is it like
Someone studied the rotation of the fish.
nice? That's good to know.
That's pretty much
All right, I'm looking for something with the least amount of symmetry. Yeah, let's look over here. So let's say we were just talking about like a fish like flying through space. And like if we roughly said a fish looks like an ellipsoid, like some kind of oddly shaped sphere. Why are there, so it's coming up in a second, why are there 3 different moments of inertia for our ellipsoid fish? Why are there 3 different ones? Okay, so moments around X, Y, Z. What would, and let's pull this up. What would a moment of inertia around X be describing? Like let's say I choose the X moment of inertia. Yeah.
So I guess it depends on whether it's spinning like
I'm trying to copy this thing.
it's spinning with A's at the center point.
Yeah.
So they're spinning around it.
So it's spinning around A. So kind of like corkscrewing through space, right? Do a barrel roll. Yeah, exactly. Doing a barrel roll. Versus like if I took the y-axis, I'm talking about like front flips. Yeah, back flips. Like somehow spinning like that. And then Z is like totally spinning like, I don't know what to call that. Yeah. But spinning around. And in general, like if something's spinning without other forces acting on it, without other constraints, it's around its center of mass. Like it's not going to spin around its tail, even though you change the axis. I won't jump like too far into like how spinning works in 3 dimensions, because the main thing that I wanted to get across here was like whenever you choose your moment of inertia, you're also choosing what axis you're spinning around. So in the case of this Tesla, I chose like the front of the hood and it's corkscrewing through the air, which is different than like doing donuts as it flies through space, like spinning around the other axis. If you choose something like a sphere, then it's like sphere is a sphere. It's always one moment of inertia. But yeah, so thanks for bringing up the fish. Thanks for all the fish. No. So the middle M is yo-yo, little M mass, and big M is your payload mass. Yeah.
Why is your big R equal to your double V? So your payload radius equal to the weight of the car?
That one, so big r is your initial yo-yo radius.
Oh, I see.
Yeah. So really, I should have said w over 2. So if I mounted it like to the rear view mirrors, like side view mirrors.
Yeah.
But instead, I mounted it like somewhere out here.
Yeah. This.
Yeah.
Okay, I see. So I was doing like the radius somewhere.
Yeah, or like the radius plus space elevator, like, or whatever. Yeah.
Yeah, okay, cool.
Okay, that's a good one. Yeah.
Just trying to figure out, maybe I'm just doing it as a solid.
Oh, the solid. Why not empty? You're assuming.
I'm trying to do, yeah.
Okay.
Well, I'm just based on the creations as well.
Yeah, because I think
So which,
wall thickness is.
right, and then which equation.
Oh, I guess because I was thinking like handles going here.
What do you think you're going to do? Do you want a little more weight for ours?
I guess we could.
So we get it.
Yeah.
I was just gonna do the earth as well.
Other.
I feel like.
That's fine. You can hit it. Should be okay.
I think I make this too big, so I make it like 1 times 100. So like what you want.
Yeah.
And then maximum size.
Well, yeah.
Just delete it. And then we find
Blue veil. Okay. That should work. Yeah. Blue dot.
1,000 kilograms.
Yeah. Yeah. That's how big it is. 3,000 kilograms. A lot.
It's a lot.
Yeah.
I looked it up. It says 90,000 tons, 36,000 kilograms. Wow. It's huge. 190,000 kilograms.
Aluminum? Yeah. Okay. Yeah, just see them. Yeah, just kind of despawn. Okay. So. Yeah. Search up. Yes. Yeah. Figure out mass. Yeah. Are you supposed to like do max in each extra one?
Whatever Campbell wants himself.
The sun? Oh, yeah. Yeah.
That'd be a little more towards that.
Is the sun rotating?
Yeah, well, also, you know, the sun rotating, I believe that single solar day is, I think it's 10 hours.
The sun rotates once every 10 hours.
I think so.
Yeah.
What is that big
So big M, here I'll go up and tell everybody.
Big M was like the Tesla.
Yeah, big M is your like payload. And then here, let's take a look at this. So some other parameters here,
7 days.
like big, 27 day. So big M is the mass of your payload, and then the little m is the mass of your yo-yo, like what you're actually using to de-spin. Then there's also this little thing, I mean it's not little, big uppercase R is where you're mounting your yo-yos. Here I called it W, but really I should have said like W/2 to like, if I wanted to put it on the side view mirrors or like on the car doors or something. I don't know why I just said like W, because now it's like somewhere outside the car when it would make more sense to like keep everything inside to start. But yeah, so the yo-yo, the main things that affect it are like what are its mass, where am I mounting it, and then how fast am I rotating before I start despinning. Yeah, and there was where am I looking? There was one idea of like, oh, what if we had a hamster wheel that was, again, totally safe, it has oxygen, has fuel, but my question was, oh, are you going to add a point mass for like the hamster in there? And do you know what the parallel axis theorem is? Technically it's part of the prerequisite for this class, but I mean, you use it once at the end of the semester and then never hear the word again until now. Do you remember what parallel axis theorem? The name is good. I guess I should write out parallel. So in terms of our, like, how parallel axis theorem works here is like, let's say you have an object, but you want to add a moment of inertia from another object. And really this is how, like if you were actually trying to figure out like what is the moment of inertia of my spaceship, you would build a giant CAD model, assign densities to every piece of the model, and then use a computer parallel axis theorem to sum up all the contributions from each individual little element. So the I of hamster plus the ball is I of the ball plus mr squared of the hamster and hamster. So we're splitting it up into saying like the ball itself is some kind of like thin sphere, 2/3 mr squared. Then we'll add up the fact that we have a little hamster. Somewhere outside that center of mass. And if we want to be more, like really the fact that we have a mass inside there is going to change the center of mass by a little bit, but it'll like shift the location slightly, but that's okay. We'll just but that's parallel axis theorem in a hamster ball. Quick reintroduction to the idea. As long as you're using the same rotation point for everything. You can add, same way that you would add mass of like, what is the mass of my car? Well, it's the mass of me plus the car plus the gas. You can do the same thing with parallel axis theorem if you're using the same rotation point. And another one, we were talking about like Gampel Pavilion. I like those triangles, but I'm trying to figure out, how do you even draw them? I don't know. I don't know how to draw them.
I guess draw lines and draw something.
Yeah? You think that would work? I'd still get squares. Maybe if I connect all those. Something like that. So we got Gampel. We could say that Gampel is like a hollow kind of cylinder plus, oh, whoops, I put a plus sign, plus this dome on top, or 1/2 times 2/3 mr squared, because it's taking a sphere, cut the sphere in half, and you get half the moment of inertia, something like that. At least if you want. Or you could say, the roof, it's barely anything compared to all the concrete of everything else. It's like, and you're probably valid in saying that too. But that's what we're going for today. It's like, how do we take a real object, simplify it enough where we capture its dynamic properties. Oh man, we're almost at the time.
Yeah, so payload plus the yo-yos are something. Yeah, at first the yo-yos are rejected. It go. Now the only thing that makes the yo-yos to payload is also. And so there's centrifugal. This is where centrifugal force is a very real thing.
Oh, is this building not the initial
That's the initial angular velocity of everything together.
Okay.
And the yo-yos have nothing to
This is
do
the
with
massive,
Yes. Yes.
and this will be moment of inertia.
Probably because once they run out of fluid, you don't want them.
That would just be so like some W, some rate.
Yeah. The equation for it is the equation for the moment of inertia for a rectangle is y. But this is, I guess you said this is the compensation.
I mean, that's a real formula for the solid. You might be looking at the second solid. Like this is the same as the solid, right? And it's squared over 6 is 6, and this is e squared plus e squared.
Yeah, so we need to change. This is
W equals of inertia that is described. And that has to do with bending. Yeah, yeah, mechanics and materials they use the same vocabulary.
Three dimensions. This here is, wait, but if this is three dimensions, then what about the depth?
Yeah, what about that?
No, I was.
Yeah. Well, in this case, the depth would change how heavy it is, but it doesn't change how mass is distributed around that cross. Yeah. Well, it's not the cross section, it's the total object, but doesn't change like how mass is actually around the axis of rotation.
I'm just trying to make it else.
Yeah. Yeah.
Why is the inertia equation used as the way I equals big why does it take use?
Oh, yeah, that one's just like capital. Sorry about that. Yeah. You're right, because that should be a capital. Yeah. Just grabbing the same function. Yeah, that makes sense. Yeah.
So the C should be a capital letter.
C.
No.
Where's the C?
You have it. It's here. You have C equals. What is this state?
That one is.
There is this.
Yeah, there is a C. Yeah.
Should that be a capital letter or that's a
No, that one's like a two-step solution of like set all this stuff equal to something. You can call whatever thing you want.
Okay.
And then in order to figure out how far you're going, you get square root C and square root C. Yeah,
That's
yeah. Yeah, that one's just something. It doesn't really matter what it costs. Yeah, paper.
we're supposed to choose the
Yeah, you can choose any paper. Yeah.
Okay.
Yeah.
The yo-yo. The yo-yo is
And then, so the idea is that in this case, there's a Tesla spinning in space using the yo-yo T-spinner. So you can get anything. And
What's
spin
in
your phone.
using it?
Yeah. So it'll be different massive noise, but same analysis.
So I have to choose something that's basically it's big.
I mean, you can choose whatever you
That's
want.
it. Does this change the I?
Yeah, change like
What anything? Is this use I is the same IX or IY?
No, it's different. So if this was like top end over end, like flipping through space, I would need a different set of yo-yos.
Okay, so you're saying that this is only rotated in like the X and Y.
Yeah.
Or is it direction?
Yeah, it's close.
Which X? Which X? Like this one?
Yes, at least in this case.
Just pick one? Or
Yeah, you pick it. Or like what would it look like in space? And that one, like even engineers say, it's a choice. Like you don't need to be in a rocket that's spinning this way.
yeah.
It's only a quarter.
So you want to no longer have the yo-yos after 6 months. You're
When I was doing this, my craft day, I got 2 points. Yeah, 1 point. So now we're probably using that. So we have in space 0 to 1. So I'm changing that to like 1 to 3. Because it's probably. Longer now.
Yeah, so try to increase that.
You could keep increasing it.
Or I mean, I could also make it bigger or something.
You can make weight bigger. If you look at the last one, it tells you what TF is. Yeah, you can run that one. You just keep going down until you get the printout.
2 questions. Is the cord that is, as the project is spinning,
Yeah.
the cord that is, does it come from the center cord or from the side?
So it's gotta come out something, it's gotta come out. If it's 0, there's no centrifugal force. So we're never gonna leave your station.
What I mean is, if it's spinning,
Yeah.
you have the 2 balls on the side, and the strings that connect the balls, so. The strings, are they coming from the center or are they coming from the side? Because like, say this is your spinning yo-yo.
Yeah.
So the cord was originally from the side here, you go back around.
Yeah, in practice, that's what happens. You gotta wrap it around.
But in this instance, is the cord attached here or is it attached here?
This would be like a mat, like, really we're kind of simplifying it, so we're taking your whole payload and just saying like, it's gonna wrap around some kind of radius. Really, it could be like a spool.
So it is attached here, it's like slowly unspooling.
Yeah.
We just go to something, and second, also, when it comes to the work side.
Yeah. Have you submitted anything for notes? Okay, for each assignment, you say like when you're turning it in, you can reach out to
Let's hear your contact.
It's all on SBC. Yeah.
Okay, I'll send you guys.
Okay.
Thank you. So I'm gonna have these numbers right here. Yeah, I just said.
Yeah, see how it's millions of seconds?
Yeah.
So if you want to see the whole path to go to its release, you need at least that number of seconds.
Okay, and I mean, I could probably decrease that if I had.
Yeah, more than
150. That would actually apply.
Yep.
Ahead of time, programs or whatever that you know wants to be.
Again, it's probably gonna be like some ratio, like we're looking at 1200 to 0.01.
Yeah.
Probably means, at least if you want it to last like a second.
Yeah. Usually we'll be waiting all the time, it's 10 to 24.
Yeah.
Alright, thank you. I'll start doing that.
Thanks.
Easy. You just